Hello again. To pick up from where we started, in this video we are going to discuss how computer vision handles real-time data processing in ADAS. I already emphasized the importance of real-time data processing in ADAS and also told you that computer vision plays a very important role and a pivotal role in understanding the real-time data processing. Now we will see how this is going to achieve that. Now, computer vision enables real-time data processing in advanced driver assistance systems through combination of specialized hardware, optimized algorithms and sensor fusion. Okay, now how does it work? First is with the help of high-speed hardware architecture. And what are these high-speed embedded hardware architectures? Embedded vision processors, dedicated chips like Texas Instruments TDA 2X or NVIDIA Drive process 1920 to 1080 resolution video at 18 to 30 frames per second, performing trillions of operations per second to meet strict latency requirements, which is less than 100 milliseconds. Now coming to the edge computing, onboard GPUs and telematic processing units analyze data locally and avoiding cloud latency. Okay, so this graphic processor unit and telematic processing unit, they avoid the cloud latency. And for example, Mobileye's IQ5 processes 24 tera operations per second. This tera operations per second for simultaneous object detection and scene segmentation. Okay, now when it comes to optimized algorithms for low latency, now how does what is this optimized algorithms for low latency? You use lightweight CNNs like models which include models like YOLO. They prioritize speed by analyzing the entire frames in one pass, achieving 45 to 60 FPS on the embedded hardware. Alright, so you achieve 45 to 60 FPS when compared to the 18 to 30 FPS of the embedded vision processor. And this lightweight convolutional neural networks, with the help of this 45 to 60 FPS, it very much reduces the latency. Now coming to the selective frame processing, dash cameras store only critical events to conserve bandwidth using motion triggered analysis. Alright, so the dash camera, instead of storing the entire entire drive, it only stores the critical events. That way it can conserve the bandwidth. Next is parallel processing, and multi-core architectures split tasks across cores to maintain real-time performance. Okay, so it split tasks like lane detection by pedestrian tracking across cores to maintain real-time performance. Now next thing is with the help of sensor fusion and redundancy. Okay, so and how does it achieve sensor fusion? With the help of multi-model inputs, it combines camera data with radar, lidar to cross-validate distances and reduce false positives. For example, radar supplements in CV for foggy conditions. Okay, so with the help of this multi-model inputs, so usually computer vision means it is only with camera, but sometimes it combines the data which complements or supplements the CV in the foggy conditions. Next comes the redundant systems. Fail-safe mechanisms ensure continuous operation. If one sensor fails, that means stereo cameras backing up lidar. Now coming to adaptive workflows for dynamic environments, the dynamic resolution scaling, it reduces the image resolution in low risk scenarios to save the processing power. Alright, so this is like proactive image resolution, where risk is low, then it reduces the resolution to save the processing power. So you don't require any high resolution when there is no risk. Okay, so this computer vision can identify whether it is a high risk scenario and low risk scenario and proactively changes the image resolution to save the processing power. And coming to the context aware processing, it prioritizes critical tasks over non-urgent ones. Again, this is a very proactive mechanism where it prioritizes critical tasks. For example, emergency braking is there. So this is an SLD functionality. So naturally this prioritizes this critical task using reinforcement learning. Okay, so based on the context, prioritization happens. Now when it comes to real world applications, please understand this table. ADAS features, this I already touched upon, so I will just touch upon this performance metric. When it comes to automatic emergency braking, reaction time is less than 0.2 to 0.5 second. When it comes to lane keeping assist, latency is approximately 10 milliseconds. And when it comes to traffic sign recognition, with the help of efficient net B3 classification, accuracy is 98.7 at the rate of 30 fps. Now challenges to solutions, challenges and solutions. What are the challenges? First is the computational limit. So quantization, reducing neural network precision from 32-bit to 8-bit cuts power usage by 40% without accuracy loss. So naturally when you reduce the bit size from 8-bit or 32-bit to 8-bit, general perception is you may lose the accuracy. But there is a new mechanism called quantization. Even though it is reducing from 32 to 8-bit, it cuts the power by 40% without any accuracy loss, and this is a huge advantage. Now when it comes to environmental variability, multiple spectral cameras, they maintain detection in the darkness and glare. Now one of the biggest disadvantage of the camera is it cannot work in the dark, and this multispectral cameras, which comprise of this infrared plus red green blue, maintain detection even in the darkness, thereby complementing thereby nullifying the disadvantage of the camera. Now when it comes to data load, this spatio-temporal filter ignores static objects to focus on the dynamic threats. And by balancing speed and accuracy through hardware software co-design, computer vision ensures ADAS system react faster than human drivers, critical to preventing up to 40% of the collision. Okay, so this particular sentence gives you a overall umbrella type summary, the importance of the real-time applications and how this real-time applications is happening in computer vision. Now let's briefly touch upon the role of the deep learning in computer vision for ADAS. When it comes to deep learning, the deep learning revolutionizes computer vision advanced driver assistance system by enabling accurate real-time interpretation of complex environments. So this is exponentially learning. How does a ECU exponentially learn? It learns and it implements. Okay, just like as a human being learns, as he becomes more and more experienced drivers, as he navigates in more and more difficult scenarios, he naturally learns how to drive in more and more complicated scenarios. Likewise, the ECU or the computer or the HPC, it learns with the help of the computer vision. And how does it do that, and what are the core contributions? First is enhanced object detection and classifications. Okay, so pedestrian and cyclist detection models like YOLO and faster RCNN analyze camera feeds to identify obstacles with 95 to 99% accuracy, reducing false positives by 40% compared to traditional methods. Okay, so with the help of deep learning, you are reducing the false positives by 40%, thereby enhancing your accuracy. Now when it comes to traffic sign recognition, CNNs classify signs even in low light conditions, achieving 98 sign accuracy at 30 fps. In the previous slide, I told you, with the help of infrared spectrum camera, the traffic sign recognition or low condition recognition is drastically improving. And also when you combine that infrared spectrum with deep learning, it enhances the accuracy to 98.7 accuracy. Now when it comes to sensor fusion and environmental modeling, it combines LiDAR, radar and camera data to create 3D maps, estimating object distances with less than 10 centimeter error margins. It also predicts trajectories using LSTMs to anticipate collisions 2-3 seconds in advance. Alright, so it predicts the trajectory and it anticipates the collision 2 to 3 seconds advance, which gives ample time for both the computer and also to driver to prevent the accident. Now, when it comes to real-time data decision making, it processes 4K video at 30 to 60 FPS on embedded GPUs, enabling sub 100 millisecond response times for emergency braking. So, when you are able to process a very high data stream which comprises of almost 4K, and the two at a rate of 30-60 FPS with the help of GPUs which are manufactured by NVIDIA, it reduces the latency below 100 milliseconds. Now, coming to optimizing computational load via quantization, reducing power consumption by 40% without sacrificing accuracy. Now, this is something you learned even in the real-time working of the computer vision. So, deep learning is also complementing this accuracy. Now, when it comes to key deep learning architectures in ADAS, alright, the task is lane detection, UNet CNNs, but performance is 99.1, accuracy in fog rain. And next comes the driver monitoring, vision transformers, which is acronymed as VIT. It detects drowsiness in 0.2 seconds. And coming to multi-object tracking, deep sort plus YOLO, it tracks 50 plus objects simultaneously. So with the help of 50 plus objects tracking, this can interpret the traffic scenario to the very high level of accuracy. Understand this very carefully. This multi-object tracking is with the help of deep sort plus YOLO and tracking 50 plus objects simultaneously. It is drastically making advent into the automotive market, so because it can perceive or interpret the traffic scenario with high level of accuracy. Now, when it comes to workflow integration, well, first is data processing. It augments training data sets with synthetic fog layer to improve robustness, and it normalizes sensor inputs like radar, ladder, point clouds, radar echoes for consistent analysis. And next comes the hardware optimization, employs models on edge devices like Texas Instruments TDA2X, which deliver 4 tera operations per second per watt efficiency. Now, this is able to do this many operations per second with a single watt. This is very important. This is where this hardware optimization comes into picture. And also it uses tensor RT for model pruning, reduces ResNet 50 size by 75%. Now, let's see the continuous learning. After data processing, you optimize the hardware and then you learn continuously. Implements OTA updates to refine models with new edge cases, and it employs semi-supervised learning, cutting annotation cost by 60%. Now, how does it impact the safety? How can you identify the metric based on some safety metrics? It reduces the collision rates by 40% as per NHTSA through proactive braking, and it lowers lane departure incidents by 55% via precise lane boundary detection. So you can understand how much the efficacy has improved because of this deep learning. By enabling the systems to see and react like human beings, but faster, it does not only see and react like human beings, but even faster it does. Deep learning forms the backbone of modern ADAS, bridging the gap between the full anatomy. So as deep learning is becoming more and more efficient, as the efficacy of the deep learning algorithms are becoming more and more accurate, this can act faster and better than human beings, and thereby making the full autonomy dream a reality. Okay, thank you.